So, welcome everyone to our session on industrial IoT and connecting existing machines to tomorrow's Internet of Things. I will go into details what we mean by that title. But before that, I would like to introduce myself. My name is Markus Besterhorn. I'm an IoT Business Development Manager for AWS. I'm today joined by Jan Metzner, an IoT Specialist SA for AWS, and Kurt Gatzka from Deutsche Bahn. But before we go into the details of this session here, I would like to walk this backwards from you, my customers, today, and show you what you are going to take out of this session. There's a lot of talk about Industry 4.0 and digitalization of industrial processes. And we have the pleasure today to have Deutsche Bahn with us on stage, who are going to describe their use case and how they built a digital twin on top of AWS. And in the second part of this session, we are going to go deeper into technical details. This is a level 300 session, so you can expect some technical details where we will show you how to access industrial machines and how to do that with Greengrass and our AWS IoT toolbox. And in the last part of this session, we will show you a design pattern that has been very successful with customers. One of them, again, is Deutsche Bahn, for extracting this kind of data and actually making sure that the right data gets to the cloud. Not just everything, the right data. So when we talk about Industry 4.0, it's often mentioned that there are lots of people working on it, and there's lots of money spent on various fronts and with companies thinking about how can they make this happen. Now you would think, so many people working on it, smart people, what's the success of this? And there is actually research that has looked at how good are companies, how far are they along this journey with Industry 4.0. And the picture that this research has shown is, let's say, not so well. Because we see it here, we usually can't link the data together. It's difficult to access the data. And these two go kind of hand in hand. If you can't get to the data, if you can't exit it, then you're not going to be able to really link the data together. If you have two sensors that sometimes report something, or where you can't even get really to the data and have to make something up or find a workaround, that's always a difficult thing when you want to have insight into something that is valuable for your business. Now, considering that there are so many smart people working on this and there's so much money spent, you could ask yourself, why? Why is that not really becoming a reality already? And with a bit of humor, but there's a grain of truth here, that's really a good picture for this. The industry, manufacturing industry or production industry, has been very good at making standards. They started in the 70s and 80s with something like Modbus, for example. It has been around longer than I'm on this planet. So there has been really starting to develop different standards. Some companies have kind of made it a go-to-market strategy for themselves, that they said, okay, we are going to invent the new standard, and eventually everybody is going to follow it. There have been several attempts at this, and none of them really worked. But it just added to the heap of standards and protocols that we have today in industrial manufacturing environments. Now, what's the result of this? If you go to the average shop floor or to any company that tries this, you are going to see the following. You have a machine that has several components, like a PLC here, industrial PC here, an I/O coupler here, and they will all talk different standards. They will all talk different standards, something that somewhere along the road this has been defined as a standard. Now, you have this in a single machine. But if you think about the picture that I had on the first slide, there is usually not a single machine. You have more machines. And what does it mean? Well, more machines means more standards, more protocols, more things that really can't interoperate with each other. And when you look then at a whole shop floor, you get a zoo of protocols. And it's very likely that you have a lot of these different standards on your shop floor. And the challenge now is you want to make use of the data on your shop floor and get it somehow into some state that you can make it understandable in your IT environment. You want to have knowledge about, for example, you want to compute the KPIs of your production line here. Can you do that? Is that easy? Apparently it's not. And this is one of the key challenges. So everybody talking about predictive maintenance and all of that, this is the requirement. This is a requirement to get there, because if you don't have the data, you can't do predictive maintenance or any of these nice things that you could, derive from that. You can't even compute your KPIs correctly without having that data. So this is the core challenge. And one of the companies that has faced this is Deutsche Bahn. And I'm honored to ask Kurt Gatzka on stage today, and he will show you a bit of their use case on building a digital twin with AWS. Thank you.
Yeah. Thank you, Markus. Thank you for the invitation. I'm Kurt Gatzka, and I'm responsible for the DB IoT Cloud at Deutsche Bahn. As the largest European railway company, we do have exactly these challenges. And at the same time, we see IoT as one of the main drivers for digitalization. In the following minutes, I would like to talk about how we address these challenges, and that physical connectivity is only one part of the challenge. Let's have a look at our assets, or better in this context, let's have a look at our things. We are operating more than 6,500 passenger trains running in and between cities. And we do have more than 37,000 miles of tracks. And to make traveling more comfortable, we operate more than 5,500 train stations with a lot of things inside, like electronic displays, tickets machines where you can buy train tickets. And our cargo fleet has more than 80,000 freight wagons. And of course, we have maintenance site. We have maintenance site all over the country, and at Deutsche Bahn, we are more than 300,000 employees, so we do have a lot of office buildings, and they're getting more and more smart, like your smart home. And our train engines need energy, so we are also an energy company with a huge network and a lot of smart meters, for example. And here's the conflict. Nobody wants to wait for a delayed train, and at the same time, he wants to have the latest update. Or you want to find a free and available seat, and at the same time, we do allow last-minute reservations. Or our cargo customers want to have just-in-time delivery, and at the same time, unexpected things are happening. And we would like to operate our fleet in the most efficient way. So that's why things have to communicate with each other. The train has to communicate with the train station to provide the latest update, or a broken freight wagon has to communicate with the maintenance side so that the workers can get prepared for the next repair task. And that's exactly our challenge. How can assets communicate with each other, or how can things communicate with each other across all business areas? We do see the digital twin as a solution, and in the following, let's have a look at what the digital twin is and what is our vision of a digital twin ecosystem. I will make an example with a freight wagon, but you can also imagine another thing like a car or a plane, what you might be more familiar with. We are installing sensors at freight wagons, like load sensors or GPS sensors and telematic devices. And these sensors collects data about the wagon, the freight, and the load, and the environment. The sensor data is sent to the cloud. And in the cloud, we create a digital identity of the physical asset. And we store that sensor data as this digital identity. And then we call this the digital twin. So we not only just store the data like mass data, and we connect the data to the digital identity. And now This digital twin, on the one hand, we have the physical asset, and on the other side, we do have the digital twin in the cloud. We just talked about sensors which were directly attached at the asset, but at the same time, information can also be gathered by other sources. Imagine a camera which somehow recognizes the wagon. And pictures, for example, can also show an information about the wagon, the condition about the wagon, like damages. And we are also sending that information to the cloud. That might be supported through artificial intelligence services or recognition services. And with this additional information, the capabilities of the digital twin grows. Another typical example are RFID sensors, which are installed at the tracks. Every time when a wagon passes these sensors, the wagon ID is transferred to the cloud. And because we exactly know the position of these sensors, this also provides an information about the location of the wagon in that moment. And we can use this information and we can combine it, for example, with the GPS sensor. And the combination of the GPS signal and the RFID sensors increases the correctness of the digital twin's position data in the cloud. And now applications can use this digital twin data instead of the single sensor data source. So that the value that the digital twin delivers now is higher than just the value the single sensor data source delivers. Now we can work and interact with the digital twin. We can use the attached data and we can store new information at the digital twin. Information the physical asset might even don't have. For example, the health status or the estimated time of arrival. The estimated time of arrival is a good example. Imagine you are standing in front of a physical freight wagon and you want to know when it arrives at the next train station. So you could ask the freight wagon, but you won't get an answer from the metal. But at the same time, if you would ask the digital twin in the cloud, this twin might give you back an information, a calculated information. So now the digital twin has a value that the physical asset don't even have. We do create digital twins of different assets or different things in the cloud. And with the DB IoT cloud, we allow them to communicate with each other so that the train engine can communicate with its wagons or the train engine can communicate with the train station. I could talk much more about this, but actually that doesn't fit into this session really. So that's the interesting part here. But in the future, the digital twin ecosystem may have even more value than the physical assets in some cases. So the question, in our opinion, is not if we do need a digital twin. The question is, when do we need a digital twin? If we remember the picture of our assets and our things in the beginning and imagine an ecosystem of digital twins, we need connectivity and to a highly heterogeneous physical world of devices and things. So that's very important to make this happen, this vision. I brought an example, and this is a typical example and one of the first examples we realized with AWS, and it shows a track inside a maintenance site. And at both ends of the maintenance site, you see an RFID scanner. So this RFID scanner has a proprietary connection to the RFID controller. This is a small green device here. And the RFID controller is connected to the edge device running AWS Greengrass. And the edge device is connected to the DB IoT cloud, which is based on AWS. So every time when a wagon passes these scanners, the wagon ID is transferred to the cloud. And before it is processed by the edge device, and the edge device transfers this information to the cloud. And there it updates the twin position of the wagon, and it updates the digital twin of the maintenance site with its parked physical wagons, or better, with its parked digital twins. So how does it look like in reality? That gets a better imagine. That's a picture of a maintenance site, and you can see the tracks in front of the maintenance site and some wagons, and you can imagine that GPS sensors are not working so good that you get the exact location of a wagon and the right order of the wagons on the tracks. And if you look inside a building there, you see a typical wagon, and because of the metal roof of the building, also GPS sensors are not working, so we need the other source of information that we can locate the exact position of the wagon. This is just as an example, a small RFID sensor. It looks quite big, but it's just that size, so it fits into your hand. And these are the RFID scanners on both ends of the track, and they can recognize the wagon IDs from a few meters. And this is a technical installation on site with the RFID controllers. Here are a few more controllers, so there are some more tracks than just one. And you see that little orange or orange-red device. This is a small server running AWS as Greengrass. This picture shows just the same setup, just in 2D. You see, again, the components, the RFID readers, the RFID controllers, and the edge device with the two important AWS components, the Modbus protocol converter to get connectivity to the RFID controller, and the AWS Greengrass, which connects to the AWS IoT core running in the DB IoT cloud, which provides there an important functionality. So now you got an idea of the digital twin and how it can communicate in the twin ecosystem, and why connectivity is so important to reach this goal. And now we should have in a much more technical detail how the AWS components are working. So thank you very much, and Markus.
Thank you, Kurt, and maybe a short round of applause for Kurt. And
thank you.
So you already see it here. There's a Modbus converter that tries to convert whatever comes out of that box into something that AWS IoT can use. And now we want to take you on a journey how to do these kind of protocol conversions, because that's the bar that you need to jump over when you want to access the wagon track data or your machines or anything that similar to that. So let's go back to that abstract picture that I had in the beginning about the shop floor, but this can also be your maintenance site or some building. And in general, you will have, in this case, factory machines or the RFID readers, to be more specific. Now, the first thing that you need, as done in the Deutsche Bahn case, you need a gateway. You need something that allows you to access the internet, because most of these components or factory machines, they run protocols that are not internet ready, as I would call them. They have, like Modbus, it has like zero security. All the other protocols are usually not made for being directly exposed to the internet. So you need that gateway component also maybe for having like a mobile router or something like that you can get internet access here. And then AWS Greengrass has a very important functionality that is deploying a Lambda. So those of you that are familiar with AWS, Lambda, you're asking yourself, Lambda IoT serverless, how does this fit? With Greengrass, you're able to deploy Lambda scripts that you've written, just like the serverless logic that you usually use with Lambda, and deploy it on the edge, like a Python script, Node.js, Java, all of that. And you can write a script, for example, that converts you OPC UA to data that is understandable by IoT core. For example, MQTT messages that you can send. So that is something that we have on our homepage as an example in Node.js, but you can also use Python for this. There are very good libraries. We will go into that. Now, of course, you can write a Modbus conversion and convert that. So you see already there's a certain pattern here. You can write different scripts for converting this. And of course, if you have something proprietary, we will use today a TCP here for a camera, actually. And then you can convert that and send also the data from this to the cloud. And last but not least, if you have something that already talks MQTT, of course, you can also do that. So that's what you do on the edge. And once you have that, you can actually stream the data to AWS IoT core. And that allows you to connect the whole thing to your IT systems. So here you see the connection, and in the next couple of minutes, we will try to focus just on that protocol conversion and how to usually do that with AWS Greengrass. And for this, I will ask Jan Metzner on stage, and he will run you through a demo on data extraction with Greengrass.
Thanks, Markus. Let's switch over. So again, welcome. We have I've built a small demo to show you how to connect industrial devices. Markus already told you the general pattern, which is actually we need to know, obviously, how to connect to the device. So we need to know the protocol. When we know the protocol, we need to have a library to actually talk the protocol. In the simplest way, which we use in the first place, is actually just TCP, which most of the programming languages have in there. So we talk this protocol, and we read the data, and then we actually publish the data internally in the Greengrass system. Okay. So the first thing what you need to know is actually I need to connect to the device. Okay. So we have here a few things. Let me just show it to you. No, sorry. This one here. Need to be a little bit careful because otherwise you will not see too much. So you see this guy here? This is actually a recognition device from a company called SICK. We have such devices, for example, in our fulfillment centers. They can read barcodes, QR codes, and so on and so forth. So similar to what Cord actually explained in his talk, you need to recognize something. So how do we connect to this guy, and how do we extract the data? So first of all, we need to know a little bit what's going on. So let's see. There's a program to actually talk to this unit, and it will just show me actually what's going on. So I have here on this little cube a QR code. Okay, not very fancy, it's just a QR code, and we just try to recognize that and get the data out of the QR code into the cloud. So what do we do? We just need to check, okay, what's going on. There's a live view in this program, so let's see what the camera is detecting. So it's very small, but you see on the bottom here, the QR code that was detected has some content. It's called reInvent 2018. Okay, so we actually want to take this data point and move it to the cloud. So the interesting part is that this device is actually exposing a simple TCP API. So if I connect to the device, I will just see, okay, a data stream of TCP messages flying through, and it's actually just text, which I can easily extract and funnel that to the cloud. So how would you do that? We need to write a Lambda function. So Markus already told you, the piece that we will do here is having a process, that's a Lambda function, running as a single process that will connect out and just do this. So I've opened Cloud9 here. So Cloud9, our development IDE, so that you can see what's going on. So let me show you the Lambda function to actually connect. Let me make it a little bigger. To connect to the device. So we are connecting here. This is Node.js code. You don't need to know what the code really does. So you don't need to be a Node.js developer. Just in general, what's going on here. We are connecting actually to this device. So it has an IP address. It is actually the same IP address, if I'm changing back here, which I discovered here. So I will switch back here to to the IDE. And then for every piece of data that we see here, we just receive it. And in this line, actually, we call the internal publish functionality inside Greengrass and publish this to the Greengrass system. Okay? So that is more or less the adapter between the non-Ethernet protocol, the non-PubSub protocol, and the internal messaging protocol inside Greengrass. So as long as you can have a protocol and a library, which you can actually use to talk this protocol, you can more or less convert that. If you have a non-message-based protocol, it's a little bit more complex, but in theory, you can actually talk any protocol. So how would you deploy that? If you have never used Greengrass before, you need to create a Greengrass group. So what you see here is the configuration of a Greengrass group. A Greengrass group consists of a Greengrass core, which actually holds the logic. The configuration consists also of the Lambda functions. It consists of the message flow. So Greengrass is more or less a type of a microsystem environment where one functionality here is just extracting the data. The next thing would be maybe transferring the data or preprocessing the data. In this talk, we will just look in the connectivity. So what I need to do is actually, I will just configure this Lambda function to be long-running. I can show that in a second as well. And then forward the data to the cloud itself. So now we should actually see the data that is flying in. We just had a little bit of problem. We'll talk about this later on. So what you see here is we have a kind of industrial environment set up as well. So you see here, there's the switch. We have a router here as well that goes up into the internet. On this switch, we have actually this IPC connected. So this is similar to the device that Kurt explained. So it's a simple IPC x86 where Greengrass is running on. So it's connected here as well as the SIG unit is connected here as well. And in this way, we can talk to the industrial machinery and just extract the data. So now I would like actually to see the data flying in. I don't know why, but something happened while we moved the stuff from my hotel room down here. Because at least right before the session, we were not seeing. Oh, we see data. Okay. Things happen. Okay. So what you now see is the extraction of the data that was transferred to AWS IoT. Here, this is a test console inside AWS IoT. So you see the data that is flying inside into the cloud itself. And you see on this topic that there were a data point. The data point is no read, because there was no read beforehand. If you move it back, okay. So let's see, we should actually see some. Okay. You see something actually I've not explained yet. So here you see that. It has a high frequent, the reads are very high frequent, so that we really tag if the conveyor belt works. So you see that here it recognized actually reInvent 2018. So we get the data. You see a lot of unstructured data as well, but you can extract that. So we have a separate function to extract the data out of the raw data that we receive from the SIG unit. But it's kind of easy to do that. And you can even do much more. You can then do, if it's more than just text data, obviously you can pre-process the data. You can do something like averages and so on and so forth. So this is the simplest way to have, okay, the pattern is I extract this device, I extract the data, and I'm publishing it internally into the Greengrass system. So let's see how we do that with different protocols as well. So you have already seen something. There's a little bit more going on here as well. Let me switch here. Okay. So you see here a PLC. That is the standard back-off PLC. Yes, now I know why. Yeah, okay. That's a standard back-off PLC. And we have a small robot, actually, and a distance sensor. And we have the conveyor belt. And we have, so you see a small, let's say, robotic cell that is operating and recognizing something. It recognizes a code. And it simulates actually a drill simulation. So what happens is actually that I can connect to the PLC itself, and it is exposing data. So let's see what data the PLC is exposing. So this is a back-off PLC, which means it exposes an OPC UA server. Okay, here we are. So this is a standard OPC UA client. If I would have an industrial network, I would take this laptop to the industrial network. I will plug it in. I will connect to this guy, and I would be able to see the values. The values are exposed because somebody that has programmed the stuff has actually named it in this way. And what you can do with this client is I can just monitor what's going on. Okay? So this is just the data that is exposed here by the PLC. So let's see what the cell it's actually exposing over OPC UA. So you see the conveyor belt is running. You see actually that the robot is stopped, but now it's in motion. You see that the drill, okay, it's not drilling really, it's just simulated data, but it's simulated the drilling process. So it goes up, it cools down now, the robot moves back, and then the conveyor belt starts. So actually, those type of data we want to have actually in the cloud. So we will do the same thing what we have done with the raw TCP data, just with a different protocol. So let's go in there. So again, I will open an IDE. If you look on our sorry, here we go. So if you look in our documentation, we have the possibility, and we launched this a year ago, to connect to OPC UA server. There's a sample application on our GitHub to show you how you could do this with an open source library. I'm using this easy sample. In a production scenario, you would need to maybe also use a different OPC UA library. This is a library which we can easily distribute from a license perspective, but it will actually serve the purpose. So what it does actually is, this is the configuration. You see I'm connecting to the server. Again, I need to know the IP address, which I get actually from hopefully the guys that programmed this or everything. So it's the same IP address which you see here on the client. And then I can do subscriptions. So for that, again, I need to know, okay, what type of data do I need to extract? So these are the data points that you see here in the client. So you see actually the node IDs, these are the absolute node IDs that I'm subscribing to. So then you see these are the IDs that I have configured in there. And in the rest of the code, you can just take it as it is from our GitHub repository. I will just quickly show you what it is doing. Okay, there's an OPC UA subscriber, and there's a separate topic, a separate file. And in this file, you will actually find that it will publish data to AWS IoT. In AWS Greengrass. So you see this part here. So this is the same part that you have seen before with the TCP data. It is just publishing, but in this case, actually, it's publishing a JSON document out of the single node update that happened actually from the OPC UA server. So this is a piece where you actually more or less take the data and publish it internally into the Greengrass system. So let's look into this. Let's look into the console as well. And I will do another subscription. Quickly check. So data appears here on OPC UA/something. So let's start it again, because if there's no update, you will not see anything. Let's put the camera here as well, so that you see what's going on. Let's put it in between. And now let's start this stuff. You see that there's data coming in, the robot is changing, and we actually connected to the whole cell. We extracted the data out of the machinery, and we actually now have the live data more or less in the cloud. You have seen that especially on the drilling process, you get a lot of data. So this is just the connectivity. So we will probably not transfer all the data like it is to the cloud. You will batch the data, or you will even just do some averages on that, and then transfer the data to the cloud. But again, the initial thing is to connect to this and extract the data. It's the same pattern as we have had before regarding how complex the protocol is. Still, you need to understand how to connect to the device and how you need to actually extract the data with a certain protocol. So once you have this, you will see that you can configure inside Greengrass way more things. But here you see the simplest way where we are just publishing every data point to the cloud. Again, in this real scenario, we'll have something in between in order to just save messages and bandwidths, and also to have context. Because a single point, a message like that, something like, okay, in a single point of time, the pressure of the drill will not help you that much if you don't know actually which product was currently produced, and so on and so forth. So you will combine that probably in enrich it with more metadata in order to have all that in the cloud, because otherwise you would need to do that later on. Good. So the third thing, what we actually wanted to show, but it didn't work well. I don't know if you have seen it. We have announced on Monday, not announced, it's public already, that you can connect directly to certain protocols without writing a Lambda function. I will not I can't show it because something didn't went well, but it's called Greengrass connectors. And we talked about Modbus before, and there is actually a way to use Modbus without writing a Lambda function. So if you see here, we have now a bunch of different connectors already in there, even third-party connectors. And if I have a Modbus RTU device or a serial connection, I can actually just take this connector, configure the connector, and I can send a message to the connector, and I will get the message back. So if this would be a Modbus I/O coupler, for example, I could just send a message, hey, switch this and this and this I/O on and off, and we'll get a message back, okay, acknowledged, and it is done. So we are going into this direction where you don't even need to write all those connectors, or you can even write some of those connectors. You see there are also some third-party connectors in there, so that we are supporting also third parties and partners on our platform. Okay, so that was the small demo that just showed you a little bit how that would look in an industrial environment. Obviously, in a real scenario, it's way more complex. You have way more devices to connect. You have seen actually that I can either connect to the guy that is controlling everything, or can even bypass this. It is even possible to take the images from the camera and push it to the cloud. So depending on the device itself, you can configure that. Okay, then we just need to switch back to Marcus and go on. So thank you very much.
Okay, let's see. Okay, good. So, sorry for that. Apparently, it's not only industrial equipment that's difficult to connect. So what Jan has shown you is basically this architecture here. He's shown you that basically we used OPC UA in this case, extracted data with a relatively simple or easy to obtain extraction script. We've seen their data from the field bus devices. We've seen data coming in there from the camera, the QR code scanner, the conveyor belt, as you've seen, the stuff that moves this box here. And we've also gotten data from our mini drill here. So that makes it possible to get data out of your shop floor. Of course, other protocols, as stated, Modbus is obviously also possible, and there are many more. It also works seamlessly with our shadow. So if you want to control something, that's very handy, because you can also use the shadow and ask the shadow once there's a change to trigger a Lambda function and then do a control, for example, for a light. So it also works the other way around. You can write protocol converters that actually write into your industrial equipment. While many of our industrial customers are very, very careful with anything that flows into their shop floor, for certain things like when you want to control something like a light or a warning or something like that, that is actually something that is useful for the customers. And this is just so that you're aware that it's not just one way out. You can also do it the other way, if the protocol permits it. So what did we show you? First of all, we've shown you some way of getting data out near real time, like historic data As you've seen, we could push the changes of the drill, for example, while it was drilling, the state changes of the conveyor belt, also even with really high frequent data. So that's really important. If you want to capture something that goes wrong, then that is very handy. But of course, also state information, like the drill, was it working or not working, and so on, is really important, because sometimes you just want to have the drill data when it's actually working, and that allows you to make decisions and capture data when it's relevant. And all of that can be combined to a digital representation of this highly professional production environment here, or the train wagons of Deutsche Bahn, or a building of the Deutsche Bahn, or anything else. So you can use that data to do this digital representation or digital twin. So that's really what we wanted to show you, how to get over that initial step of extracting data. Now, we've only shown you the first step, because what you usually want to do in IoT, and this is the pattern that we would like to show you, is what we call ETL at the edge. And ETL, anybody, is probably a term that is quite familiar to those in a different context, but it has the same meaning. You can apply these software design patterns that you're used to from the cloud and use them on the edge. We've shown you only the leftmost part, the extraction part. But for example, if you remember what we got out of the QR code reader, we had a lot of garbage in the simple read. So you could remove all of that garbage in a second step with a transformation. Or you could already turn that into some JSON format or something that is really usable. If you think about why would I not do that in a single step or a single Lambda? Well, maybe you have several outputs of a single Lambda, and that goes into different topics that you want to handle differently. And also organizationally, sometimes you have different teams that are responsible for different parts. So for example, the extraction part is usually done by those experts about the machines. But the transformation is already something that maybe your data science people would like to control, because they are interested in the data usually in a certain way or certain format. So they would like to control what kind of data gets into the, for example, the data lake or whatever they use for machine learning. So they want to sit there and do the transformation. Now, the last part, and that's the load part, the L of the ETL, that's something that you usually do and with looking for cost, for example. You want to buffer certain things, you want to do some compression and stuff like that, and then you load that to the cloud. So if you do that with Lambdas, you can separate these responsibilities also inside your organization, and each part is responsible just for one piece of that pipeline. Just like you do it often in organizations that develop the ETL pipeline for a company. So this is why we recommend our customers to use this approach and this design pattern for also implementing their industrial data extraction from the edge to the cloud. With that, I would like to wrap things up here and would like to conclude this talk. We've shown you how to do, or in this short period of time here, do a data extraction in a simple way. We've given you the basic parts. It's always like get the library that talks this protocol, write a Lambda script, and wrap this into a Lambda, and then deploy it on the edge and run it on Greengrass. That's a relatively low bar to solve this problem. So it's not completely solved, but it's still in a way that it's manageable and becoming easier and easier to cope with this challenge. The approach is basically applicable to lots and lots of protocols. We've shown you today just two, also with looking at the time. We've used two protocols, TCP-based protocols, but you can also use, as you've seen, there is already an RTU Modbus connector. So you can also use serial protocols. You can access the hardware directly. And if you have anything that is able to provide you with a serial data, then that's fine as well. And now to the part on the right side here, everybody should start and say, okay, we are not bound anymore by this problem. We can actually, it's handled. You can handle it by using this approach for accessing your industrial data. It's a solvable problem, so I recommend start building. Start going ahead with your Industrial 4.0 projects and push this so that you can actually get to the point where you have digital twins like that. Of course, AWS will help you. We have various sources for that, solution architects, prototyping teams, but also all the online resources. For example, the OPC UA script that we saw, you can load it directly from our homepage. There's actually a nice tutorial how to do that and how to do this whole OPC UA extraction with that Lambda. With this, I would like to. This is the last repeat of this section, but there are some related breakouts. I don't have the updated version, but the middle one is definitely one that is very related to this because it shows you what you can actually do with the data. It is a workshop. It's a level 400 workshop for those that are deeply technical. And it shows you how to derive a machine learning model based on data that you would get from such a machine. In this case, I think we're using OPC UA data.
It's on Thursday.
It's on Thursday, so it's tomorrow. With this, thank you for your attention. And before we wrap up, I have asked for everyone that was here, please vote, because it's very important for us to see which sessions are good for our customers, which was not so good, and then this drives or has a huge impact on next year's reInvent session. So if you like something or didn't like something, then please let us know. Of course, the technical problems are something that we should avoid in the future. So with this, thank you for your attention and have a nice evening and a rest of the week.